Hi EP Chem class, this is Hoover. Hi, this is your solutions video to the winter assignment. I'm not going to do every question. I'm going to kind of give you hints on how to do some of them, but you should, from the instructional video and from the notes, be able to do these problems. And I'll just give you some tips on how to do them on some of them, and some of them I won't do at all. Okay, let's get started. So this is due Friday, January the 8th. It's not due as soon as you get back to school, so don't sweat that, but try to get it done before we get back to school on Monday, January the 4th, because we're going to have a busy week with another subject then. All right, so here we go. We're going to start off with some formulas at the top. I'll deal with these later. These come in later in the assignment, and these constants, we'll talk about those. Okay, so at first the first part of the couple pages really just reviews what you learned in physics if you took physics, and if you didn't, then you'll learn it here. All right, so we're talking about waves, and light is a wave. All the energy we get from the sun is waves, and it's this kind of wave that goes kind of up and down like a roller coaster called a transverse wave. The wave literally travels through space in that fashion. To give this a mathematical equivalent, these waves are sine waves. So what you learned in Integrated Math 3 or Pre-Calc or whatever math you're in, beyond Integrated Math 3 or beyond, these form sine waves. They actually travel through space in a sine wave pattern. So if we take this wave and say that it's moving to the right, so it's the wave direction is to the right, and we say that this is u, and you're standing at point A, so point A and u don't move. You just stay above. But at the beginning, as soon as you start your stopwatch, you're above a crest of the wave that we're going to call crest 0. And then 2 seconds later, the wave has moved to the right, so that now you're above crest 4. So it's like a before and after picture. All right, so we're going to ask some questions about that. All right, so let's go through this. I don't know how many of these I'm going to do. I'll do, as many as I can get through. So what's the cycle of a wave? So let's just use one of these waves as an example. A cycle is going from a crest or any point on the wave to the identical point on the next wave over. So if you start at a crest, you go down and back up to that crest. That's one cycle. It's one entire movement through the wave, okay? Now you got to be careful. If you were to start here, what would be one cycle? Well, you wouldn't just go up to here and come down to there. That's not it. You got to go down and then come back to that same point right there. That would be one cycle. So up, down, and back up again. That's why it's easier to just view it from the crest. Start at a crest, you end at a crest. Down, back up. That's a cycle, okay? Okay, so you can write this out, what I just said, and I'm going to move on. What is the wavelength? The wavelength is the straight line distance between 2 points on the wave. Again, just think in terms of crests. So it's actually what you would measure distance in. Some meters, micrometers, nanometers. Nanometer is a very common one we're going to talk about in this unit, but it's just the straight line distance. So both a cycle and a crest, you can say a cycle and a wavelength rather, you can say start at a crest and end at a crest, but they're different. One of them is a distance. It's measured in units of distance. The other is simply a number. How many times did it go up and down? So if I do this, 1, 2, 3, 4, that's 4 cycles right there. Okay? All right. Let's keep going. So again, you can pause the video and write these answers down as you need to. Okay. What are the crest and trough of the wave? So we just talked about crest. The crest is the top of the wave. The trough is the bottom. You almost never hear that term. It's technically what it's called. You'll hear the word crest quite a bit, but you never hear the word trough, okay? No, people don't refer to it very much, okay? But that's the bottom of the wave. Crest, trough. All right, what is the amplitude? The amplitude is the height of the wave from the center line. So from here to the top is the amplitude. It would also be the same as from the center line to a trough. That's the same distance as from the center line to the crest. Okay, that's the amplitude. Don't make the mistake of thinking it's from a trough all the way up to a crest. It's not this distance. It is not this distance. It's from the center line up to here or from the center line down to here. That would be the amplitude. It's the height of the wave. Okay, how many cycles from crest 1 to crest 4? So you're starting here and you're ending here. So count that. 1, 2, 3. Sometimes students make the mistake of saying, counting how many crests. 1, 2, 3, 4. That's not right. It's not how many crests. It's how many times did it make a full movement. 1, 2, 3. That's 3 cycles. Okay, if the distance from crest 0 to crest 4 is 12 meters, what is the distance of one wavelength? So if here to here is 12 meters, well, divide 12 by 4, and that means this would be 3 meters, 3 meters, 3 meters, 3 meters. Therefore, the wavelength is 3 meters. But I want you to explain that. If I write the answer down, don't just write down what I'm writing down here. I'm just giving you the answer. The wavelength lambda equals 3 meters. We haven't gotten to that symbol yet, but we will. Lambda equals 3 meters. All right, so write that out as a complete sentence or show the calculation as well. All right, next. At time t 0 seconds, crest 0 is below you at point A. 2 seconds later, crest 4 is below you at point A. What is the frequency of the wave? So that's what this picture is depicting. Crest 0 is below you. 2 seconds later, crest 4 is moved below you. So how many cycles? 1, 2, 3, 4. How long did it take? 2 seconds. So frequency, and again, you get this formula from the video. Frequency, which is designated by the Greek letter nu. It looks like a V, kind of a VU, a V or a U. It's nu, and that's simply defined as cycles per second. So in this case, that would be 4 cycles over 2 seconds. So that equals a frequency of 2. And 2 what? The unit of measure for frequency is hertz, or 2 seconds to the minus 1. This is the one you learned in physics class, but this is also a valid one. Or 2 to the 1 over seconds. Okay, so any of those are the same thing, the unit of measure for frequency. Okay, what is the period of the wave? So period is t, and that equals 1 over the frequency, which is nu. And again, I mentioned in the video that for frequency you use the letter F in physics class. You know why they couldn't, or the chemists and the physicists couldn't agree on one letter or the other? I don't know, they just couldn't. So this is the same as what F was in physics class. It's nu is the same as F. So it's 1 over the frequency is the period, and I'll let you do the math on that. Here's your frequency right here. So figure out what the period is. And the unit of measure is in seconds. That's the T kind of stands for time. Capital T stands for time. Okay, let's keep moving. If the wave has a constant speed and frequency, if a wave has a constant speed and the frequency of the wave increases, how does this affect the frequency of the wave? I think that I was supposed to say, so let me change that. How does that affect the wavelength? So there's a formula that relates frequency, wavelength, and speed, and it's wave speed, which in this case, all we're dealing with is the speed of light. Electromagnetic waves always move the speed of light, and c equals 3 times 10 to the 8th meters per second, okay, equals lambda times frequency, and that's nu. Okay, so what it's saying is if this increases, and these two have to multiply to be the same number, which is that, then what has to happen to this? Well, if this gets bigger, this has to get smaller. So the wavelength decreases. So lambda is wavelength, and that decreases. Okay, how does it affect the period? Okay, well, if the frequency increases, so whatever frequency is, so if, let's just pick some numbers. Let's say the frequency goes from V1 or nu 1 equals 5, and nu number 2 equals 10. So that's the frequency increasing. So what would happen to the period? Well, it would go from 1 over 5 to 1 over 10. That would be the period. Okay, so what that means is it went down. This is a smaller number than this. So if frequency increases, period decreases because they're the reciprocal. So it decreases. Okay, how does this affect the amplitude of the wave? It does not. Amplitude has nothing to do with the wave speed equation, and it just doesn't. So no effect. Again, I want complete sentences, okay? Don't just copy down my 2-word answers, all right? Just so we can get through this a little quicker. Okay, here we go. All right, an FM radio station has a frequency of 88.9 megahertz, And I tell you something that they would not tell you on the AP exam, so be sure you know a megahertz is 10 to the 6th hertz. It's a million hertz, or cycles per second. What is the wavelength of this radiation in meters and nanometers? Well, they only gave you one number to work with. It was this. Okay, so how do you figure out wavelength? Well, because you know that a radio wave is an electromagnetic wave. Therefore, it has the speed of light. It goes at the speed of light. And we're going to use 3 rather than 2.998. It's not really necessary to go to 4 sig figs on this. Let's just stick with 3. That's simple enough. The reason generally on an AP you wouldn't want to do that, you would want to use 2.998 or whatever they would give you on their cheat sheet, is because you want to have the appropriate number of sig figs. Now our final answer is limited to 1 sig fig because I'm only using 1 there. Okay, but we're not worrying about significant figures right now. Okay, so the speed of light is 10 to the 8 meters per second. All right, and they give you a frequency. That's new, and it's 88.9 times 10 to the 6th hertz. Okay, so we have this formula that's given to you in the video. It is the speed of light equals the wavelength times the frequency. I'm going to solve this for the wavelength is what they're asking for. So wavelength, just divide both sides by frequency, and you get C over frequency right there. So that's going to be wavelength equals 3 times 10 to the 8th over 88.9 times 10 to the 6th. And again, remember to do this. If you don't want to just do the whole thing on your calculator, you're not comfortable, you divide the coefficients and you subtract the exponents. If you feel comfortable doing the whole thing on your calculator, you can do that, all right? I'm going to do it that way because I think you understand. So you don't understand, don't feel comfortable, it would be 3 divided by 88.9, write that down, and 10 to the 8th minus 10 to the 6th, or 8 minus 6. Okay, but I'm going to show you on the calculator how you do it. Whenever you're doing scientific notation, always enclose it in parentheses. Okay, so I've got parenthesis 3 times 10 caret 8 close parenthesis divided by open parenthesis 88.9 times 10 caret 6 close parenthesis and equals, and it gives us 3.37. Okay, so the wavelength is 3. Now 3.37 what? You got to know what units you were dealing with up here. This is meters per second, and this is 1 over seconds. Okay, so the 1 over seconds is going to cancel with seconds, so you end up with meters. All right, and that sounds kind of long. You know, that's like 10 yards on a football field, right? That's a fairly long wavelength, but radio waves are typically long. They are typically long. Okay, they can be up to a mile long. So there's your answer for that, okay? Okay, U.S. Navy has a system for communicating with submerged submarines. The system uses radio waves, again, at a frequency of, okay, so there's 76. Again, you could say hertz, you could say s to the minus 1, you could say s to the 1 over s. So that's our frequency. What is the wavelength of the radiation? Again, same question as above. So you have, you know, the speed of light because it's an electromagnetic wave. And of course, what you're looking for is wavelength, lambda. Okay, same equation. You can do the work on this one and go ahead and come up with an answer. All right. Number 12. Let's go. Okay, violet has a wavelength. It's not violet a girl, it's the color. Violet has a wavelength of about 410 nanometers. What is the frequency? Calculate the energy of 1 photon of violet light, and what is the energy of 1 mole of violet photons? Okay, there's a lot in that question right there. So let's talk about these equations. I'm actually going to have you write out what each one of them means. In fact, why don't we do that now? Because we're getting into these. I probably should have put that question before we started working with them. So let's go ahead and do that. So here it is. It says write each of the 6 equations above, meaning on the front, and explain what it means. What variables does it relate? Okay. So let's just start with the first one. Again, and I'm just simply going to go 1, 2, 3, 4, 5, 6. Go straight across like that, okay? So you can see that for yourself. So C equals lambda times nu, okay? And it relates okay, number 2. Let me read it actually first. So speed of light equals wavelength times frequency. So it relates the wavelength and the frequency to the speed of light. Okay, number 2. This is energy. This one, let's just write it down first. Okay, so this is the energy. And it's good to write the subscript photon. It's the energy in a single photon of light. And if you watch the instruction video, you should be watching that first. It's a packet of light. Light can either be expressed as a wave, and that's what you learned in your physics class last year, or as a packet. That's something you probably didn't learn in your physics class, like a little ball, like an object almost. And it's a little difficult to grasp that. I think students always at first try to relate those two. But they're really, it usually either behaves like a little particle, like a little ball, or behaves like a wave. And you don't treat it as both at the same time. I know it seems like a little crazy, but it's just the way you have to kind of accept it. But this equation actually does relate it. This is the frequency of the light, or of the electromagnetic wave in general, and this is how much energy is in one photon, one of those little packets or one of those little balls. And they're related by Planck's constant, okay? So this equation relates Okay, so this equation relates the frequency of a wave, in other words, when you're looking at it as a wave, to the energy in a single photon. That is when you're looking at it as a particle. H is Planck's constant, and that equals 6.626 times 10 to the minus 34. That should be 34. And the units of measure on Planck's constant is joules seconds. Joules times seconds. Okay, let's move on. Let's do this one. Okay, so this relates the wavelength to the energy, whereas this one did the frequency to the energy. This does the wavelength. It's just a simple little algebraic manipulation of these first two equations. If you solve for nu and then plug it in, what you get there into that, you'll end up with this. Okay, so it's just basically transforming it into a relation of wavelength and energy. Okay, now we get to this one. All right. So what is this? Well, first of all, the first thing to realize is these are constants. R is the Rydberg constant, H is Planck's constant, and C is the speed of light. So this is a constant number. So what they did nicely, this was done by another instructor in Los Angeles who I know. He just combined them all into a single constant right here. Since they're never going to change, these three are always going to be constant. That's what this equals up here. So it's pretty simple. It tells you this is the Bohr equation, and it tells you what the energy is of an electron at a particular energy level. And this is simply an integer value. So in other words, at a particular orbital. So what's the energy in a first orbital electron? What's the energy in a second orbital electron? What's the energy in a third orbital electron? That's all it tells you. So you basically take this constant, this number right here, and divide by, let's say you wanted to know the energy of an electron in the third orbital, you would just plug that in 3. 3 squared is 9. So you take this number and divide it by 9, and there's a negative sign on it because you always show the energy on electrons as being negative when they're inside of the atom. And it's just the convention to do it that way. And so that gives you your answer. So it's not, it looks like a scary equation, but it's not really that bad. So let's go ahead and write that out. Okay, so if you want to know in hydrogen, and this is all for hydrogen, but that's all we're studying here. If you want to know what the energy is in an electron, a hydrogen electron that got promoted up to the third orbital by having energy put into it. You just plug the number in 3 there, and this should have a negative sign on the front of it, and just use those 3 constants that you were given and figure it out. And the energy is going to be expressed in joules. Energy is always in joules when we're dealing with this. Okay, next up. All right, this is wavelength equals Planck's constant over the mass of a particle times its velocity. This is the one that deals with the fact that particles, just think of a tennis ball or a soccer ball, actually moves in this wave-like pattern. It seems strange, but it does. And the wavelength is super, super short if you're dealing with a large object like a soccer ball, especially if you're dealing with a very large object like the Earth. It's imperceptible. But for electrons, it's actually something the size of an electron. It actually can have a perceptible value, something that you can measure. That's because the mass in the denominator here is so small that this can actually have a measurable value. Okay, so it's de Broglie's equation, so let's go ahead and write that. Oops, and I didn't write it down. I'll go ahead and write it down here second. And of course, it's going to be something much bigger than a soccer ball like the Earth, as I said. So, in other words, light, you think of as a wave, but it actually has this particle characteristic that we call photons. Little packets, little balls of energy. So it acts like a particle, like a thing. Whereas de Broglie's equation says, wait a minute, if it's true in that direction, it can be true in the other direction. And so if you have an object, an electron, a soccer ball, the Earth, anything, when it moves in a wavy pattern. And that pattern is given by this equation right here. All right, so that's what de Broglie's equation says. Okay, finally, this big, long, ugly one, but it's not a very hard equation when you think about it. RH is simply this, okay? It's this number right here. N1 is the orbital that you're starting at, and N2 is the orbital that the electron is finishing. So if it falls from, say, the 4th orbital down to the 2nd orbital, this would be 4, this would be 2. If, on the other hand, it went from the 2nd orbital up to the 4th orbital, this would be 2 and this would be 4. So it can go in either order. But basically, it's just saying that this constant times 1 over the 1st orbital minus 1 over the 2nd orbital, when you get that calculation, that gives you the reciprocal of the wavelength. So you have to finish the problem by flipping that number, taking the reciprocal, because you don't want the reciprocal of the wavelength, you want the wavelength. So you have to flip that, whatever you get over here, flip that, and that'll give you the wavelength that will come out. So this is what tells you what wavelength of light you get, is depending on which orbital it falls down from and to. Okay, so this is called the Rydberg Equation. Sometimes the way they write this in books is they just put the wavelength on top, and then they take this whole figure and they put it underneath 1. So 1 over this. That would be the wavelength. But the way this is written, it's that, and then you get 1 over the wavelength, so you have to flip the wavelength. You can do it either way. It doesn't matter. Okay, so it's that. And they put RH there. I just put R. Okay, so the Rydberg equation gives the wavelength of the wave that is produced when an electron falls from a higher to a lower orbital. Remember, if you drop a rock off out of a window, when it hits the ground, that energy is going to be released. You're going to hear some of it as sound energy. It might cause the rock to bounce a little bit. That some of the energy goes back into the rock. Some of the dirt below scatters. All that is the release of the energy. So what happens when an electron falls to another energy level? It releases energy as well, but in the form of an electromagnetic wave. That electromagnetic wave has a certain wavelength. And that wavelength will tell you what kind of wave it is, whether it's a gamma ray or X-ray or a visible light, what color visible light. So you're going to see us do some examples of this. Okay, so those are the 6 explanations for that. All right, so now we're going to go on and continue where we were before. All right, so violet light has a wavelength of 410 nanometers. So I'm going to go ahead and write that as I read this. Wavelength equals 410 times 10. This is what you ought to do. As soon as you see nanometers, write it as 10 to the minus 9th meters. because all of these constants require that things be in terms of meters, not in terms of nanometers. One thing you'll notice here is that you don't have a number between 1 and 10. We said you're supposed to do that in scientific notation. But the visible light spectrum, the red to blue light that you can actually see, is always expressed in nanometers, and it's always in hundreds of nanometers. They wanted the standard to be nanometers for the exponent, so it is hundreds of nanometers. It just happens to be the way they do it. You could write this as 4.1 times 10 to the minus 7th, but they don't want that. They want it to be in nanometers, okay? So what is the frequency? So again, we have speed of light. Okay, and they're trying to find frequency that's nu is what? Okay, so here's the equation. And if I solve for nu over here, I get nu equals c over wavelength. So that's going to equal and the wavelength is right here. Okay, remember how we cancel units in fraction over fraction? You have meters in the top of the numerator cancels with meters in the top of the denominator. They both have the word top in common, so they cancel. That means what you have up here is 1 over seconds, which is the unit of measure for frequency. We said that, right? Okay, so that number will be, I'll do this calculation with you. Okay, so it's going to be this. Okay, and it's 8 minus negative 9. You'll come across that combination very frequently because it's the speed of light's exponent and the negative 9 for nanometers. So 8 minus negative 9 is 17. Okay, but we got to move the decimal over. You notice this time I'm not doing it all on my calculator. I'm doing it the way that you might do it. 3 divided by that gives us that. Minus 9 gives us that. Now we're going to move the decimal over 1, 2, 3 places to make it a number between 1 and 10. So that's going to be 7.32 times 10 to the, we made this number bigger by moving the decimal from here to here, so we're going to make this number smaller by 3 places. That's 10 to the minus 14th, and it's hertz, or you can call it 1 over seconds, or whatever you want to call it there. Okay, there it is. So that's the answer to that. Calculate the energy in 1 photon of the violet light. So now we can use either of these two equations, the one that uses frequency or the one that uses wavelength, either one, but what we're shooting for is this. This is the energy in 1 photon. All right, so let's go ahead and use the wavelength one. Let's use the frequency one. It's easier now that we know the frequency. So this is for the second part is E equals Planck's constant times nu. Okay, and that's going to equal 6.626 times 10 to the negative 34. I think as I said, I think it's the smallest exponent in all of science. Okay, and that's joules seconds, joules times seconds. And then the frequency is this. And again, let's go ahead and convert that to 1 over seconds. Remember, we can call frequency the unit of measure 1 over seconds. Okay, that's an S. Okay, so that's going to be the 14th, 1 over seconds. Okay, so seconds on the bottom cancels with seconds on the top. You're left with joules, which is the unit of measure you want for energy. So the energy, and I always like to write the word photon as a subscript to remind you, it's the energy in 1 photon. Okay, and that's going to give you, I'm going to leave you to calculate that, okay? So be sure you do it correctly. And it looks like you should get some number in the range of 10 to the minus 19. So something, and it looks like it's going to be about, I don't know, 5 point something, 6 point something times 10 to the minus 19. So you go ahead and do that, see if that's what you get. Okay, finally, what energy in 1 mole of violet photons. Well, since it's asking that, I got to go ahead and do the calculation. That's no fair. To the negative 34. Okay. And I forgot my parenthesis. I always want to use parenthesis with scientific notation. Times 10 caret negative 34, close parenthesis, times, open a new parenthesis, 7.32 times 10 to the caret to the 14th, close parenthesis, and that gives us 4.85 times 10 to the minus 19. That's a 19. Let's do it right. Okay, there you go. That's the energy in a single photon. Then they ask energy. Okay, finally, the last part is asking, what is the energy in 1 mole of violet photons? Okay, I read the question wrong and started to do the problem wrong, so I'm going to do it again here. So you've got 4.85 times 10 to the minus 19 joules per photon. So we're going to write that out. And how much is 1 mole of photons? It's 6.022 times 10 to the 23rd photons per mole of photons. So we're going to write that out. A mole is 6.022 times 10 to the 23rd of anything. In this case, we're interested in photons. Photons per mole. Okay. So photons cancels, and you end up with joules per mole. That's how much energy in joules you have for 1 mole. So you basically just multiply these two numbers together. Okay, and that's 10 to the minus 19th, and that's 10 to the 23rd. And I'm going to leave that for you to do. Adjust the decimal. You're going to need to do a decimal adjustment there. So go ahead and do that one. Ask me if you have questions. Okay, next up. The energy of a mole of photons of red light from a laser is 175 kilojoules per mole. Calculate the energy of 1 photon of red light. What is the wavelength of red light in meters? In nanometers, compare the energy of photons of violet light to those of red light. Which are more energetic? Well, I didn't leave you a lot of space for those 6 questions. I'm going to see if we can squeeze it in here. If not, you just grab another piece of paper. So you have the energy in a mole of photons. But to use these equations, you want to have a single photon. So you know a mole is 6.022 times 10 to the 23rd. So let's figure out if there's this much energy in 6.022 times 10 to the 23rd photons, how much is there in 1 photon? And you would simply take this number and divide it by a mole. So let's go ahead and do that. First thing I want to do is I want to convert that into, get rid of the kilojoules to just make it joules, because our formulas require that you work in joules, not kilojoules. So 175 kilojoules is 175,000 joules. All right, so energy, and that's in a mole. I'm going to put a subscript because that's not a single photon, equals 175,000 joules. All right, and let's go ahead and figure out how much energy per photon. And that's joules per mole. Let's go ahead and write that. That's how many joules are in a mole. So energy for a photon equals 175,000 joules over moles. And that's going to be over 6.022 times 10 to the 23rd photons per mole. Okay, you got moles in the numerator bottom and in the denominator bottom. They both have the word bottom in common, so they can cancel. So what you have is this divided by this, joules per photon. That's what you want. The energy of a single photon, because that's what these formulas deal with, is the energy in a single photon. So we do the math on that, and what we get is And that's going to be 2.9 times 10 to the minus 19th joules. And that's in a photon, per photon. Okay, so calculate the energy of 1 photon of light. So check, we did that. We've done that one. What is the wavelength of red light in meters? Okay, so they want the wavelength. We've got the energy. So what formula are we going to use? They want wavelength. So what are we going to use? Well, we have energy. We know Planck's constant. We know the speed of light. So then we can use this formula to give us wavelength. So you're going to solve this formula for lambda. Multiply both sides by lambda. And then divide both sides by E. And you'll end up with this formula. This is just basic algebra. Integrated math 1. Okay? So I'm not trying to fake you out here. It's HC over E. Okay, again, you multiplied both sides by lambda and divided both sides by E, and you ended up with that. So let's plug in those numbers. H6 and what I get is this, to the minus 7 meters. Okay, everything in these constants is in meters, so that's in meters. 6.85 times 10 to the minus 7 meters. So that's the wavelength of the red light in meters. Now they say in nanometers, because that's, we always express light in terms of 10 to the minus 9th nanometers. So I'm simply going to take this number and I'm going to multiply it by 1 nanometer for every 10 to the minus 9th meters. There's 1 nanometer equals 10 to the minus 9th meters. So meters cancels with meters and you end up with nanometers. So divide this number by 10 to the minus 9. And what that's going to do is that's going to give you 6.85 times 10 to the 2. Let's go ahead and write it. Again, negative 7 minus negative 9 is negative 7 plus 9, gives you positive 2. Okay? And that's in nanometers. NM. Okay? But let's write that. 10 to the square, 10 squared is 100. So this is going to be 685. So you just simply write the answer as 685 nanometers. Shoot, I keep writing an M first. It's nanometers, NM. Okay? That's the answer in nanometers. That's this right here. Okay? Compare the energy of the photons of violet light with those of red light, which is more energetic. Okay, so here's a photon of red light right here. Here's a photon of violet light right here. They are both 10 to the minus 19th. But this one is a bigger number. Therefore, it has more energy. Okay, it has about, not quite twice as much, but 4.85 compared to 2.9. It's not quite twice as big, but it is definitely more. So the violet has more energy, and we said that blue light, violet light on the electromagnetic spectrum is further to the left, so it has more energy than red light, which is further to the right. Okay, so violet, I want you to explain this though, what I just said. Violet has more energy. Don't just write this. You got to be able to explain things on the AP. Just go look at the electromagnetic spectrum in the notes and explain why violet has more energy. The fact that this number is bigger than this number tells you that it does. Okay, there we go. Let's keep going. Actually, I'm going to wrap this video and continue on another video. This is about 45 minutes right now. So we'll pick this up on the next video.